Okay, so this is some thoughts about something that they would like to study in the near future, that they already started studying. And so what is the motivation for this work? So we are in the world of weighted automata, and we are in a particular world, which is the world of commuting variables at the beginning. So you can imagine if you've seen during studies generating functions, which are very common in combinatorics, and in fact you can find applications of generating functions in the study of differential equations, dynamical systems, control theory, and so on and so forth. So the basic object of study, it would be power series. Let's take the rational numbers, and you have variables x1, xd. And the main features of these variables is that they commute with each other. Okay? So these are called sometimes, as I said, generating functions, which I think it's a very bad name because it gives the bad idea that you want to apply these functions, but this is going to be misleading. These are power series, and mathematicians sometimes they call them formal power series because you don't make any assumption on convergence, for example. But for computer scientists, I think power series is exactly what you need, formal object. And well, there are many views on this object, and here just to give an introduction, a quick introduction. For example, you can define some classes of power series using several different primitives. And based on these primitives, you can find classes which mimic somehow the Chomsky hierarchy in language theory. Like in language theory, you can imagine you have finite languages, regular languages, context-free languages, and so on. And to some extent, these classes can be mimicked also by analogy for power series. You can imagine the class of polynomials, which are those series which have finite support, or ratios of polynomials, or series, this would correspond to regular languages, or series, power series which satisfy algebraic equations. This would be the analogy with context-free languages. And so far the analogy is quite tight. You can really prove this. And then you can have more general classes, maybe which can be defined satisfying certain differential equations of a certain format. I will not go into details, but just to give a feeling. And on one hand, for example, if you satisfy a linear differential equations, you get a class of power series which are called definite, sometimes called holonomic. If you use another format, you can get some series called constructively differentially finite, an incomparable class, or maybe if you don't require any restriction on the kind of algebraic differential equations that your series satisfy, you get this class of the algebraic power series. And this is just some series which have very good motivation, for example, from combinatorics. And this is somehow interesting for us because they're usually finitely representable. And then what are the typical questions that people have asked about such classes? For example, you can ask yourself, is the class of rational power series closed under sum, closed under product? Is it closed under partial derivative? Is it closed under inverse, when the inverse exists? And is it closed under composition? You can plug power series inside another. If you're lucky, this makes sense. And these are some basic questions. A more refined question, for example, inspired from algebra. You can ask if this here, okay, this here maybe commutativity is trivial because this is how those are defined. But you can ask if you get a ring where you have zero divisors, or whether the ring is Noetherian and other properties. Maybe not need to mention all of them. Or from a decision point of view, since you're in computer science, you're not interested in decision problems, you can ask, okay, if you give me, for example, the equality problem, if you give me two finitely represented series from some of those classes, can I decide if they're actually the same series? So this is a basic question. Or a more general problem is the membership problem. If you give me a series here, is it the case that the series is already there? So you can see this generates a lot of potential open problems. And another question which I like particularly is, okay, you give me a system of polynomial or differential equations, and then you want to know whether it has a power series solution. So this is another basic problem, or you can ask for a solution that fits one of those classes. Okay, this is just a short partial view on the subject. And there is a lot of literature of these kind of problems. And here, the motivation is a starting point to try to think what would be a reasonable generalization of multivariate power series in a setting where we don't necessarily require the variables x1, xn to commute with each other. So this is where weighted automata enter the picture. So instead of studying power series in commuting variables, we want to study series, or weighted languages. And so the question is, what would be a good notion of product for series in non-commuting variables, which would reasonably generalize the classical pictures in the commutative world. So this is there. And, well, if you look at series, so now variables don't commute, so series is just a mapping from free monoid over a finite alphabet to the rational, say. And, well, if you look at those objects, you can combine them in different ways. For example, you sum them. This is totally uncontroversial. Addition is pointwise. This makes a lot of sense. But then already, if you want to define a product on series, then in the non-commutative world, many options arise. Let's look at some of them, which have been proposed before. For example, a very natural product is called the Cauchy product, which is just the concatenation product. So in finite words, the Cauchy product is just AB concatenated with C is ABC, and doing nothing. However, the simple definition, you can extend it to whole series by linearity and continuity, and this will give you the Cauchy product of series. Okay? So what are the features of the Cauchy product? Well, it's not commutative. However, it does, except for that, it behaves quite nicely. For example, there are no zero divisors in the resulting ring. And also the resulting ring has a nice differential structure. Sometimes this is called the Brzozowski derivative. If you see this derivative, this can be seen that introduces some nice differential structures in the ring. However, it's non-commutative, which means you cannot apply nice results from commutative algebra to the study of this product. So let's look at another product. Another product which is very popular as well, is called the Hadamard product. So the Hadamard product, you lift multiplication from the ring, for example, from the rationals, you lift it pointwise. In the same way as addition is lifted pointwise, you multiply pointwise. So what does it mean? That A times A is A times B is 0, because A and B are different, and this is all that there is there to know. So when you multiply two same words, you get 1, you get the same word, otherwise it's 0. And this product is useful, for example, if you want to run automata in parallel. It will correspond to run automata in parallel and produce the output as the product of their outputs. What are the properties of the Hadamard product? Well, it is commutative, which is nice. So from this point of view, it's close to classical commutative algebra. However, there are a lot of zero divisors. So from this point of view, you cannot, this is a drawback. And I don't know, nice differential structure. Here, Medellinian, I didn't even mention, but the answer is no. So this is another. So what's next? Well, there is another product which somehow combines the good properties of these two, and this is called the shuffle product. What is the shuffle product? Well, I will explain here for just two letters. If you want to take the shuffle of A and B, you sum up over all possible ways. Either you choose first A and then B, you get AB, or first B and then A, you get BA. And for longer words, what do? You do the same, but it's like you have a deck of cards. You have two decks of cards, and you want to shuffle them. Then you take all possible interleavings, but you respect the order in the input words. So the relative order is respected. Otherwise, you can consider all possible orders in which two factors can be combined. So this is called the default shuffle in combinatorics. And yeah, once you define it for words, this can be lifted by linearity and continuity to whole series. And as you can see, most things are green. So it is a commutative product, which is a nice thing to have. They're not zero divisors. And it does have a nice differential structures, which I will not explain, but like, there is a nice notion of derivation for this product. Okay, it's not Euclidean, but that's a pity. And so you can imagine where I'm leading you. So which one is the good product? So the claim here is that shuffle product is going to be a good generalization of, so series with the shuffle product is going to be a good generalization of power series in commuting variables. But here you have more options, because variables need not commute. So let me justify why I claim that shuffle product is generalizing the usual product for power series. So you get a picture like this. So let's consider series with the shuffle product. And so on one hand, we have this series with the shuffle product, this ring, where sum and shuffle. On the other hand, we have the commutative ring of the power series in commuting variables with times plus and times. And I claim that these two objects, actually, these two classes are quite related. And we need to find something in the middle that mediates between these two to convince you that shuffled series will generalize power series. What is this? This is shuffled series which happen to be commutative. So if you take any series, it may or may not have the property that it's commutative, namely that the output of the series does not depend on the input, of the order of the symbols in the input. So, for example, if the series applied to ABC gives the same, if it is commutative, it will give the same result as if you apply the input in a different order like ACB. So this is a subclass of the series, those which are commutative. And it happens to be closed under sum and shuffle. So it's a subring of the shuffle ring. And well, it's rather easy to see that in fact, the shuffled series which are commutative, this whole ring is isomorphic to the power series ring. So this makes sense intuitively because if I consider an object where the letters need not commute, but then I restrict them to those that only commute, you get exactly this. So there is an isomorphism between these two rings. So the isomorphism respects sum, which is easy, but also respects shuffle. So this isomorphism will map a shuffle of two series into the product of the corresponding power series. So with this correspondence, I can already claim that those commutative shuffled series are a good, they are the same, in fact, as power series. But then there is a correspondence also on the other side. The commutative series are not just any subring of the shuffled series, they are what is called a retraction. So there is a function, a homomorphism, which takes any shuffled series, possibly non-commutative, and it maps it to a series which is commutative. So this function is actually, I don't define it here, but if you think for a moment, it is the average function. You take a series and you sum up for every input word over all possible permutations, and you divide by the number of possible permutations. So it always gives in output a commutative series, and it has the property that the commutative series are precisely the fixed points of this function. So it is a surjective homomorphism, and it's called a retraction. So this says that in fact this is a nice, very nice subring, and once you realize this, you can use some result from logic. For example, if you prove any first-order positive first-order properties of the shuffled series, it will transfer to, it will apply to the commutative series, and therefore to the power series. So in this sense, if you prove positive first-order theorems of a shuffled series, you have generalized corresponding theorems for power series, and maybe you can prove strictly more things. So this is some motivation why this is not entirely random. So once that now you, I hope I convinced you at least partially that shuffle is a good generalization of product for power series. Then you can look at the, for example, the Chomsky-like hierarchy I gave at the beginning as a motivation. And one can try to do the thought experiment to try to lift all the definitions that you find in the books about power series and see whether they have a shuffle generalization. And this makes sense. So you can take, for example, consider those series which are finite support, and this, let's call them polynomials. Nothing to be done there, this class of shuffle polynomials. Or you can consider series which satisfy linear equations, where the product is the shuffle, and we call them rational. Or you can look at the series which satisfy shuffle algebraic equations, and you can call those algebraic. And so you get the same picture, essentially. And so since you've seen in the previous slide that the commutative shuffle series correspond to the power series, which means that, for example, if I take, a series which is in this class, and happens to be commutative, but then this is the corresponding power series is in the same class, in the classical Chomsky-like hierarchy. And this works for any of those. So you really get a bigger picture. And, well, so this is called the research program. The difficult part is to select interesting questions, because you can literally take any question which has been studied, and some of them will just go through without thinking, and maybe there will be something left which will require some insight. And at this point, I don't know what will require insights. Okay, this is what I just said, that if you take shuffled series satisfying property X, first order definable, positive first order definable, then the commutative value, if it happens to be commutative, in fact, you got the corresponding power series problem. And yes, so from this point on, this is just some suggestion possible for future research. I'm interested in trying to see, yes, what are some basic algebraic results which can be deployed for shuffled series. For example, if you have analogs of implicit functions theorem or certain characterizations of being algebraic, being equivalent to some other notion called constructively algebraic, and so on. So I will not go into details. A nice decision problem, for example, if I give you a shuffled series, this is so-called the commutativity problem. I give you a shuffled series belonging to some class, it's finitely representable, maybe algebraic shuffled series or differentially algebraic shuffled series. And I want to know, is it actually a commutative series? This, I think, is a very nice decision problem, which I don't know how to solve, even for rather simple classes. So the commutativity problem. Another problem, for example, is solvability of systems of polynomial shuffle equations. So this is the basic problem if you want to think about any logic. The solvability of systems of equations is a very basic problem. And so for power series, I know this is decidable, but for shuffled series, I don't know how to proceed, and maybe it requires a further understanding of the algebra of shuffled series. So it's an open problem. And similarly also solvability of systems of differential shuffled series. I didn't define to you what is the differential structure, so I cannot show you an example, but one can, it's quite natural. And and this is the end of this. Thanks.
Questions, remarks?
Yes. So I have a question. Power series usually can be used in several applications, and one of the applications is in combinatorics. And do you think we can define some interesting questions?
I would be interested to find those. So in combinatorics, one is usually interested in counting objects of certain property, and according to certain characteristics. It is the number of trees which have so many colors and that height. But usually in these counting problems, the order in which things happen doesn't matter. Yeah? So that's why it's naturally to to a power series in commuting variables. But one can imagine that, yeah, maybe this can model different problems where you care particularly about the order of features, but I don't have. But I do have actually, so here in this problem of solving differential equations, I think this may be quite interesting because there is the corresponding problem for power series. So if I give you a system of differential equations, and I want to know, does it have a power series solution? This is an undecidable problem. This is an older result by Lipschitz and Denef from the 80s. And the core of their undecidability argument is that since the series, the power series, the variables commute, this puts non-trivial restriction on the solutions. Because when you have a solution, it means that if you derive with respect to one variable and then the other, it should give the same result as derive with respect to the second variable and then the first. So you get some kind of diamond properties for power series solution of differential equations. However, if you take the same equation and you interpret it, okay, now I want a series solution without requiring commutativity, this diamond property breaks. I mean, you don't require it anymore. This may make the problem decidable. That will be very exciting. Yeah, it would be amazing.
Is there a computational model that messes these shuffles?
That's a nice question. So I'm not aware of many. However, for a particular class, I'm aware of a model, like a state-based model. You can define a transition graph, like a weighted automaton, infinite state weighted automaton, that produces this class here, a random part. So this class here, this would be from process algebra. There is a model which arises from Petri nets, in fact from BPP. If you consider BPP with weights, and if you think about it, how it might work, I think you will end up in this class here. You will be naturally led to write certain differential equations which will fit this format, which existed for the commutative world. And then I can imagine, if you look, for example, at context-free grammars, and instead of using concatenation as your primitive, you use shuffle, and you allow weights, so a weighted context-free grammar, but with shuffle instead of Cauchy product, then you're naturally led to the notion of algebraic shuffled series. And that would be, yes. Yeah. These are two random examples.
Can you actually in this picture say or give like, some expressiveness, like a function which kind of is a typical function for this, which would maybe separate from others? So like for power series, you could just for asymptotic reasons n factorial would separate from the rationals. You could have such an expressiveness hierarchy maybe without proofs.
Probably yes, because there is this averaging function which allows you to make every series into a commutative one, and this averaging function respects asymptotics.
But are they all just like for asymptotics?
Probably
not.
Yeah, I don't know. Probably it's a simple answer, but I don't have enough examples. It's a fresh topic.
Okay, no more questions, then thank you, Lorenzo. Sylvain, maybe you can tell something? Do you need board?
No, actually, I don't think I need it. It's going to be short. I'm not sure it's about promising future areas. I think it's about very boring future areas, actually. It's been on my mind for a while. I mean, at some point, we started doing harder and harder lower bounds for various kinds of infinite state models. And I remember fondly some things about ordered data nets probability and time Petri nets probability and hardness for new Petri nets. So these kind of proofs when you want to show very high lower bounds. And the proofs got wider and wider with every paper. in order to show those lower bounds. And I was okay. I thought, yeah, I'm reasonably convinced that what we wrote was correct. I was always thinking, no reviewer understood the proofs, for sure, pretty sure. And that we needed some kind of tools to help us with this. So I know that Jerome also has some ideas around this, because already for much simpler proofs, it might sometimes there are big errors creeping inside. But for those lower bounds, we started relying on more and more sophisticated encoding somehow. We want to encode some really complex computation, typically a Turing machine or a Minsky machine with huge values and so on inside the model. And though, yeah, we think that our lower bound proofs are correct, I'm not sure everyone is convinced always. And so I would propose maybe try to have also an effort towards formalizing those proofs. It's boring. It's
not so boring.
Okay. I think it would be useful. I don't think many people would want to do it because there's no flashy results out of this, right? It's not promising in the sense that we will solve more things thanks to it, but it's more about solidifying, right? You're making sure that what you're building on is sort of more correct. You're sure that it works. And yeah, that would be my proposal, that if people are interested in this, I know Jerome has started a project around this already. Maybe your input would be welcome to try to improve things on that front. That was all.
Thanks. Just a remark. I remember it was maybe 5 years ago, one guy, Onkolazic, mentioned that he would like to run a company providing lower bounds. So
yes.
maybe
maybe that's why he moved to AI. He noticed that this was impossible to do by human beings.
Maybe.
Right.
Yes. Wouldn't it better to write a textbook and start teaching this in order to gain confidence in the correctness rather than having that cock proof?
Yes. Some proofs, I think, because thankfully the authors of those proofs have worked very hard to make them understandable, then some proofs I think we can teach. I think the Ackermann lower bounds proofs, they've been already digested a few times, but some of other proofs which were lower profile, less interesting, I think they haven't been digested in the same way, and those would be hard to teach, I think, in that current state.
Maybe more fun than writing this form.
I'm guessing, I don't know, you two tried or whatever, but can you say anything about what kind of things currently you can verify?
So Jerome might answer, but I think it's
from a
pretty far from it.
complexity point of view, I did not work on it, but there is some interesting problem. There is some library on Coq in order to define some complexity classes. And the question is how to make the proof that your problem has this complexity class. So,
So there are libraries, for instance, for fast-growing complexity functions and basic results about their properties. So this exists already, thanks to one of the colleagues.
Yes, it exists. So it's
And
not so easy to. I mean, you need to model what is high complexity classes. So what is f omega or f some ordinals. So first of all, you need to define what is an ordinal and what is the function associated to an ordinal. So it requires some technical lemmas. So somehow a library manipulating those functions. So I'm not sure it's so boring. I mean, at some point you need to generalize your results. You need to find a nice point of view of what is a lower bound result, a lower bound proof. So naturally, we have several proofs that are completely different, but maybe some of them share some structures. I think this part is not so boring. It's not just implementing proofs done by some other guys. So I like this idea.
And you have some libraries for manipulating graphs.
So yes, we started working on a library for vector addition systems. We do not start it from scratch. We started from some library built by some other colleagues. And okay, for the moment, we just have the correctness of the recent Carpenter algorithm from several co-authors, and we we started to look for the Rakoff lower bound. The Rakoff upper bound. For the lower bound, yeah, we do not
Yeah,
start with the.
My focus was really on lower
On
bounds.
the lower
I think
bound.
lower bounds are sort of tricky, but
It's
but proof assistance might be the right tool, because typically what you want to show is that some kind of program in a very basic programming language, like some kind of bounded Minsky machines, that you are going to build a compiler from this program into your other model, which are, let's say, Petri-nets or Petri-nets with data and stuff like that. That's the core of the proof. And this is the type of things for which proof assistants are sort of good at, right?
Yes.
Showing that you have a mapping that preserves the semantics from one kind of language to another kind of language. So I think that could work pretty well.
It's so easy to make some errors on those kind of proofs. It's not completely sure that the results are correct.
Exactly.
When I say au résultat, I don't mean my result. More generally, au résultat.
So I was wondering, would it help if there were just a bigger suite of problems for these very large complexity classes that you could reduce for? Like for the lower ones, we have for example all these NP complete problems. So new NP hardness proofs can often be done in like one step, whereas for these more complicated complexity classes, you often need a step of several reductions to get where you want.
It's a small community, and yeah, you can only create so many problems. But yes, I think it's been improving, but it's true.
Okay, thank you.